chapter 11. Okay. Why? I had to write this backwards, right? Chapter 11. It looks normal, but I had to physically write it backwards. Started off like this. But I flipped my camera, but I guess it doesn't matter. Okay. Let's get started with chapter 11. Chapter 11 is advanced reactions. Now, there are a few types of reactions that we've learned about in the last chapter, with chapter 10. There's 6 different kinds: precipitation, double replacement, single replacement, all the ones like that. I wanted to separate these two into their own chapter because they're a little bit more in depth, and they each have a little bit more going on with them that we need to learn to go with. So, redox reactions and acid-base reactions kind of get separated into their own section. They're a little bit more advanced and specific to AP chemistry sort of stuff. We're also going to talk today a little bit about titrations. We've done those a little bit in the lab, but we're going to go over the math a little bit more formally today. So we're going to start. The first thing we're going to talk about is oxidation numbers. Another name for oxidation states are the charges individual atoms in a compound must have in order to be stable. When we say stable, typically we're talking about the octet rule. They want to have either 0 or 8 valence electrons, and the oxidation numbers are the charge that they need to have in the compound for that to be true. Okay? And we use these all the time. We use oxidation numbers regularly when two ions bond together through ionic bonding. So, we have some calcium and chlorine. I have calcium 2 plus, chlorine 1 minus, and those charges basically tell you what needs to happen for that to be satisfied. This calcium needs to lose 2 electrons. Chlorine needs to gain 1 electron. So we can kind of figure out the ratio that they need to bond is CaCl2. I need 2 chlorines to take the 2 electrons away from calcium. And our shortcut version of that was you take your charges and you swap them. We did what we call the swap and drop method over here. So the 2 goes to the chlorine, the 1 goes to the calcium, and that's why we're doing that, just to figure out how many of each atom I need to bond. So that's what oxidation numbers have been useful to us so far for, but they're also useful for other types of compounds. Some other ionic compounds that are more complicated and covalent compounds both need these oxidation numbers sometimes. Okay, we're going to get pretty much right into some rules for how to assign these numbers in a compound. They're not always obvious. You do not always use the number on the periodic table. This isn't really something I would have told you before, but on the periodic table, those numbers you write for all those charges, 1 plus, 2 plus, 3 plus, 4 plus or minus, 3 minus, 2 minus, 1 minus, those are the charges in binary ionic compounds. So that means that only apply when you have a positive and negative switching just 2 different atoms to make a compound. Those don't apply all the time. Okay? So we're going to learn some other oxidation charges that you might have depending on the situation. So an atom in its elemental form. Okay? So for most atoms, this is just a single atom. But for our 7 diatomic molecules, it would be 2 of them. So Fe or Br2 or O2 or Cl2 or any other of those diatomics is called an elemental form. It's the simplest form of an element you can have. That always has an oxidation number of 0. A pure atom has no charge either way. And then similarly, an ion, so something maybe I have some sodium plus floating around. Its oxidation number is equal to whatever its charge is. So sodium plus has an oxidation charge of 1 plus. If you have an oxygen 2 minus ion, its oxidation number is 2 minus. Okay? So a free floating thing, ion or atom, just has an oxidation number equal to its charge. And last, the sum of all oxidation numbers in a molecule must equal the charge of that molecule. So if my giant compound has an overall charge of 3 minus, that means if I add together all the oxidation numbers in that compound, the sum must also be 3 minus. In addition to that, polyatomic ions have their usual charges. Now, these are the rules I've given to you first. I bet this doesn't make sense, but let's do some examples and we'll kind of come back to this. You also need this information. Okay. Our problem here is that the oxidation numbers aren't always the same as you would expect on the table, But these, any of the ones on this chart, are always correct. These are your go-to oxidation numbers that you can use to kind of help you figure out the rest. Okay? When I say group 1, that means on your periodic table, the first column, the alkali metals, their oxidation state is always just like normal, 1+. So that's nice. Those are exactly the same, along with group 2. Group 1 and group 2 work exactly like they should for all examples we'll ever do. Okay? Group 2, those alkaline earth metals have an oxidation state of 2+. And that's kind of where the nice ones end. All those nonmetals are weird. We'll get next to hydrogen, and hydrogen can be bonded in 2 different ways, and it can have 2 different charges. 99% of the time, though, it'll be this first one. Hydrogen with a nonmetal has a 1+ charge. If you have a hydrogen with a metal, which is a very rare situation, it can have a 1- charge, though. I'm only giving you that. I would prefer just to leave that off to prevent confusing you. If you see an example where it's not adding up and you have just like a metal, maybe you have iron bonded to hydrogen, like iron hydride. In that one weird situation, hydrogen acts as a nonmetal with a negative charge. But hydrogen usually acts as a metal kind of bonding with other nonmetals. It usually has that positive charge. So assume hydrogen's positive unless you're getting a really weird one where it's not working out. Okay? So that's kind of so far what we need. Hydrogen's usually 1+. Group 1 and 2 are normal. Then we'll go down to fluorine. Fluorine is nice. It's always 1-. Oxygen is always 2-, unless it's in this specific compound. This is hydrogen peroxide, and in this compound, oxygen has a 1-. I don't think that's super relevant. It's just one compound, but I have seen that one specific example show up on the AP exam recently. So I just wanted to give you that information as well. And I'll give you a couple of those through our worksheets and stuff. Okay? And that's all the rules, but let's actually talk about what I'm wanting you to do in the first place. So, determine the oxidation number of each element in the following compounds. Okay, so I have all of them written out here. And what we're going to do is go through, and for every single atom, we need to write what its oxidation state is. Now, for one like this one, CaO, it's going to be relatively simple. This is an example of a binary ionic compound. You made of calcium, which has a positive charge. Oxygen has a negative charge. If you have this sort of situation, it makes your life a lot easier. This allows you to use the periodic table for everything. So you could go just like normal. Calcium is 2+, oxygen is 2-. And that's it. That's typically how we would write the oxidation states for regular ionic things. But if you look at these other examples, we have more than 2 atoms. When you have more than 2 atoms, you're going to have to apply these other rules. Okay, let's move on to the next one then. So I'm going to go through and we're going to label anything that we can. Anything that we know according to that table with our rules. The first thing I notice is this K. K is in group 1. Okay, on the periodic table, it's in that very first row, so I know its charge has to be 1+. So the K's charge is 1+. Oxygen's also on my list. Oxygen is always 2-, with that one exception that none of these are. Okay, 2-. And I have 3 oxygens. So each of these oxygens has a charge of 2-, which means you can kind of think of this as since there's 3 of them, that'd be like a total of 6-. Each oxygen has a charge of 2-. And so I know the charge on my oxygen. I know the charge on my potassium. I just need to know the charge on my nitrogen. This molecule has a charge overall of 0, right? There's no symbols for charge, which will be the case most of the time. So I need all of these charges when I add them up to equal 0. I have one potassium, which has a 1+ charge. Okay. I have a nitrogen, which I don't know. And then I have 3 oxygens, which each have a -2 charge. Okay. So I kind of have like 1 plus something plus -6 equals 0. And that means n must be 5. 1 plus 5 plus -6 gives you 0. So I know my nitrogen has an oxidation state of +5. And if you check on your periodic table, that's not what it should be. So in this example, you have to kind of use those rules to figure out what everything's charge needs to be. Let's move on to the third one. I'm going to kind of go through and label any of the ones that I definitely know. I know that the sodium is definitely 1 plus because it's in the first group. Hydrogen, 1 plus. And then oxygen, 2 minus. Those are ones, that's what you start with. There always will be some that you know, and you go in and label all of those first. Okay. Then you have to go through and figure out, okay, I need to figure out what S is. That's the one I'm missing. So I'm going to kind of add everything up. I have 1 plus 1 plus S minus 2 times 4 is 8. So I'm subtracting 8 equals 0. Right? My total charge is 0. So when I add all these together, it has to equal 0. So I have 2 plus S minus 8. S equals 6. So this S has a 6 plus charge. So you're kind of like solving a little puzzle. You can find the oxidation number of each individual atom. I'm just going to run through these last ones a little bit faster now, just so we can see it. Calcium is in that second group, so I know it's definitely 2 plus. Oxygen is definitely 2 minus. And there's 3 of them, so I'll keep that in mind. I need to find carbon is the last one I'm missing. I don't have any special rules to help me with carbon, so I have to puzzle it out using my surroundings. So this is 2 plus carbon, and then this is 3 times minus 2 is negative 6 equals 0. So 2 plus something minus 6 gives me 0. Carbon is 4. So I know carbon has a 4 plus oxidation state. Number 5 is nitrogen. Nitrogen, N2. This is a pure elemental form, right? Nitrogen is a Brinkelhoff element, so when I have 2 of them, that is just its simplest form. Its oxidation is 0. So N2 has an oxidation state of 0. That's all you need. Anytime you have a free atom, that's its oxidation state. Then I get to water. Water is actually nice here because I know hydrogen's 1 plus, oxygen's always 2 plus. And when I add these together, they should equal 0 because there's no overall charge. This is 2 times 1 is 2 plus, 2 minus, yeah, that equals 0. So sometimes we'll need to know these individual oxidation numbers of each atom because they're going to be necessary for kind of the next step. So being able to determine them, your basic process is go use that table you just copied down, find any of them that you know, and then there'll usually be one missing that you have to kind of puzzle out based on what makes it equal 0. Yeah. All right, so to summarize, to determine the oxidation numbers of something, 3 elements, go ahead and give them a 0. 3 ions, just have the charge of the ion. Binary ionic compounds, meaning normal ionic things, are easy. You don't have to do any special rules. Just use their normal oxidation states from the periodic table. But when you have these covalent compounds or ionic compounds with more than 2 elements, like most of these examples, use that chart. You assign any oxidation numbers that you already know, and then you puzzle out the rest using like some basic algebra. Okay, that leads to us this example. Determine the oxidation number of carbon before and after the reaction. So that means I want to know what is carbon, just the atoms, oxidation number over here before and when it's made in this compound. Okay, so I have it written down over here. Carbon on the left side here is all by itself. It is a free atom, so it's 0. Carbon's oxidation state before the reaction is 0. After the reaction, it's assembled into carbon dioxide. So oxygen, I know, has to be minus 2. I have 2 of them, which equals negative 4. So carbon has to balance that out. It must be plus 4. So before my reaction, carbon equals 0 plus, or 0. And then after, carbon is 4 plus. Okay. The second part of the question says, does carbon gain or lose electrons during the reaction? So let's think about carbon. Carbon before started with a charge of 0. And after, its charge went to positive 4. So your charge, you got more positive, right? You got a more positive charge. To get a more positive charge, you must lose electrons. Electrons have a negative charge, so when you lose electrons, you get more positive. So this carbon atom actually lost 4 electrons during this reaction. Okay? And those electrons end up going to this oxygen instead. A redox reaction is what we're going to talk about next. Oxidation reduction reaction, also called a redox reaction, so they mean the same thing, is a reaction that involves a transfer of electrons during the reaction. And that's the one we just talked about, was a redox reaction, right? Like we said, carbon gained 4 electrons. No, sorry, I said it backwards. Carbon lost 4 electrons during the reaction. So we transferred electrons from one to another. This transfer of electrons changes those oxidation numbers of at least 2 atoms during the course of the reaction. Now, typically, we haven't done these a lot. Some reactions are oxidation and reduction without us knowing it, but these are reactions involved with some sort of electricity or transfer of energy as a result of this movement of electrons. Remember, electricity is just electrons moving. So this reaction would create like that little bit of electricity. We have 2 vocab words that are incredibly important. First is oxidation. Oxidation is the loss of electrons during a chemical reaction. That carbon, right, just lost electrons. So it was oxidized. Reduction is the gaining of electrons during a chemical reaction. That oxygen gained those 4 electrons, so it was reduced. So it's really important to know each of those 2 words. A lot of questions would be like, which thing was oxidized in this reaction? So you're going to look which thing lost electrons. During a redox reaction, one element is oxidized while the other is reduced. You can't have one without the other because the electrons have to go somewhere. You can't just make them disappear. The way to remember this, the better way, is with the saying, Leo says grr. Leo. Lose electrons oxidation. Think of Leo, the lion, very powerful. Says grr. That's what lions say. Gain electrons reduction. Okay? Lose electrons oxidation. Gain electrons reduction. Okay? Leo says grr. Identify the element that is oxidized and the element that is reduced in this reaction. So let's take a look at it. Okay, so we're here at this reaction. I'm going to look at their oxidation states before and after to figure out which thing is oxidized, which thing is losing electrons, and which thing is reduced. So I'm just going to go through and assign their oxidation states. Calcium is by itself, so it's 0. Chlorine, it's not by itself, but it is diatomic. That's its simplest form, also 0. So both things start off at 0. That's going to make it a little easier. And we end with CaCl2. Now, calcium is in that second group, so we know it always uses its normal oxidation state of 2+. Also, this is just a regular, binary compound, so you wouldn't have to assign them all out like this. Chlorine in this example uses its 1 minus normal one as well. 1 minus times 2 is 2 minus, and those cancel out, so that's good. What this means is calcium goes from 0 to 2+. And chlorine on the left side starts at 0 and goes to 1 minus. One of them got more positive, one of them got more negative. Calcium 0 to 2+. You got more positive. That means you lost electrons. Leo, lose electrons oxidation. Lose electrons oxidized. Chlorine, you got more negative. To get more negative, you need to gain electrons. Grr. Gain electrons, reduced. And that's how you do it. Another practice. Go to the next reaction. Okay, so I'm going to try to identify what's gaining, what's losing. Okay, so I'm going to kind of look around through these. Oxygen's an easy one. It starts as 0 over here. Okay. Over here, I have hydrogen, carbon. Okay, kind of looking around. Going to try to identify, maybe I'll start with oxygen because I have oxygen 0 over here. Oxygen right here will be 2 minus, right? Because it's bonded with something. And this oxygen's also 2 minus. All right, so our oxygen is going from 0 to 2 minus. Oxygen is getting more negative, which means you're gaining electrons. Oxidation. Nope. That's why you don't skip the Leo says Ger. Leo, Ger. Gain electrons, reduce. Reduction. All right, so now I'm going to try to find the other thing. So over here on the right, I can figure out this carbon, 2 minus times 2 is 4 minus, so this one had to be 4 plus. And then over here, this hydrogen, 2 minus, this one's 1 plus. Okay, so those are what those ended with. Let's see if they changed over here at all. So this is my hydrogen over here, and it starts with a 1 plus. And there's 4 of them, so this carbon must be a 4 minus. Okay, so that carbon changes significantly. It goes from -4 to +4. It gets a lot more positive. Your hydrogen, though, 1 plus doesn't change. But your carbon, I do see changing here. So for carbon, going from -4 to +4, it's losing electrons. It's getting more positive. You lose electrons, oxidize. So there's always something somewhere that reduces or oxidizes in a redox reaction. And then I have one more example here for us to do. This longer one, I kind of ran out of room. So this is the 2 things on the left, my 2 reactants, and I have 3 products. So I see copper here. This one's easy. It's by itself. Give it a 0. And this copper is not by itself, so it will probably have a charge. I'm going to give you a little trick. Here, nitrate, NO3. You know normally NO3 has a -1 charge, and that'll stay this case here. This whole thing has a -1 charge. And there are 2 of them. So that equals -2. So copper has a +2. You can use the polyatomic ions to your advantages as long as you know their normal charges. They're not going to change. So this nitrate, also, since you know it has a -1 charge, you can just say that is the charge of the whole thing. And I can use that as a shortcut to figure out copper. Now you can also break it down and find each thing's individual charge. So for example, this would be 2 minus times 3. And then I know this has to be 5 plus, because that's how you get the -1 charge to appear. Okay? But I can use that to find that copper goes from 0 to 2 plus. 0 to 2 plus, you get more positive. To get more positive, you have to lose electrons. So this is an oxidation. All right, let me look through everything else and see if I can find anything. We're probably not looking at O's here because it's -2. This O will be -2. This O will be -2. O's always -2. So that's probably not the one changing here. Same thing with hydrogen. 1 positive, it's still going to be 1 positive over here. That means we probably have to look at nitrogen. Over here on the left, if I'm going to add all this up, okay, I have -6 and 1. So to make it balance, this needs to be 5 plus. We've already kind of talked about this one, but this nitrogen is also 5 plus. But it's not our only nitrogen. We have a nitrogen over here as well. This nitrogen is -2 times 2 is -4 is only 4 plus. So it doesn't matter if it changes everywhere. A nitrogen over here switched to a new charge on this side. It got more negative, right? It went from 5 plus to 4 plus is getting more negative. When you gained electrons, that's your reduction. So it's kind of like a weird little balancing puzzle that you have to do. Okay. When balancing redox reactions, the number of electrons lost by oxidation must be equal to the number of electrons gained by reduction. And if you look at our examples, you might not have seen that necessarily, because we didn't take into account any of the coefficients of the balanced reaction. So if we just kind of go back real quick, I can show that though. Okay. It looks like I gained I lost 2 electrons here. But keep in mind, I have a coefficient of 4. Okay. So it's really like I lost 1/4 of that, but it's a little weird. We'll talk about that. And then this 5 to 4 only has a coefficient of 2. So like it maths out. But let's talk about how to actually balance them. You can never have these leftover electrons or make electrons appear out of thin air. So we are going to do this problem. We're going to balance the following redox reaction in acidic solution. So I'm going to go through this whole process. Be warned, it kind of sucks. It kind of feels like I'm making up stuff out of thin air as we go. But this is the method for balancing these. The good news is you're not going to be asked to do this directly, but you do kind of need to know the process-ish. So I'm just going to go through one example with you real quick. I say real quick, but it takes a minute, and then you can kind of like see what I mean. So here is my reaction, and I want to balance this. But what that means is I need to make sure that not only are my atoms balanced on each side, which might feel like it's impossible because you have O's over here, but no O's over here. So we'll have to address that. So we need to balance this, add numbers to the front, okay? And we need to make sure that my number of electrons is constant on either side. So to do that, we're going to break this up into 2 reactions. We're going to look at the oxidation part and the reduction part. So what I'm going to do is write what we call a half reaction. I'm going to start with my ClO3 minus. And I want to say that turns into Cl minus. Okay. So this turns to this. I'm just kind of grouping the things that match. This has Cl, this has Cl. So I'm going to put that on one side. And then we're going to do the same thing with my other parts of my half reaction. I minus and I2. Make sure to leave plenty of room, and we're going to split those onto either side of my paper. And now we're going to attempt to balance each one separately, and then at the end, we're going to squish them back together. But it's going to make our life a lot easier doing it this way. So I'm going to start over here. You're going to go through all these steps. The first thing you're going to do is make sure you have the same number of chlorines, which you do in this case. So that's nice. So you balance all atoms except for O's and H's. So that's I'll just put that over here in case you want to write this down to have this process. Balance everything except O and H. Oops. Which in this case over here, it's good. I will have to do some work over here to balance that, but it should be easy. All right. The question said to balance this in acidic solution. And we'll learn more about what that means later. But in an acid, you have a few things floating around. Acids have water floating around. So that means I can use water in my reaction in a couple different ways. And acids, by definition, we'll learn this a little bit later, have H plus ions floating around. So those 2 things are available for me to use to interact with my reactants and products. So over here, that's what I'm going to do to balance my O's. This side has 3 O's. And to balance that, I'm going to put 3 H2O's on this side. So now my O, I have 3 over here and 3 over here. And I know it feels like I'm just pulling that out of nowhere because I am. My justification is that it's in an acidic solution and you can just do that. It's not really there anyways. It's just water. It's not really interacting. We're using this kind of as a placeholder to help us balance the electrons. That's step 2. Add H2O to balance O's if necessary. Now, though, I have my O's good, but now I added these 6 H's. But I can balance that by adding some H pluses to the other side. So I need to add 6 H pluses to this side to make it so I have 6 H's on both sides. So I'm going to add some H plus to balance. That's not even close. To balance H's. Okay, and I'll come to this other side later. I'm just doing this one first. The last thing I need to balance is my total charge on either side. So I'm just going to kind of think about it. This is 6 plus 6 and then 1 plus each. And this is minus. So this side of my reaction has a total charge of 5 plus. This side of my reaction has a total charge of minus. I need to make those equal. So I'm going to add electrons until those charges are equal. So to make those equal, I need to, on the left side here, add 6 electrons. That'll make it so these balance out, and the charge over here is also just minus. So you're going to add electrons to balance charges. And now this is a balanced half reaction. Your charges on both sides are equal. Your number of hydrogens and oxygens and chlorines on both sides are equal. That side is good to go. Repeat the process for the other one. So balance everything except O's and H's. So I need to add a 2 over here. So my iodines are good on either side. Okay. Fortunately, there's no H's or O's, so I can skip step 2 and 3 this time. I just have to go to balance my electrons. This side has a total charge of 2 minus. This side has a total charge of 0. If I add 2 electrons to this side is also 2 minus. That's another balanced half reaction. Okay. If you kind of think about it, this side, electrons are a reactant. Okay. Since electrons are a reactant, that means you are gaining electrons. So if we kind of think about it, this would have a 5 plus, so have a 1 minus. If we think about the chlorine here, the chlorine, and you don't need this, isn't really a part of it, it's just kind of a thought part, is getting more electrons, gaining electrons reduction. This chlorine gains electrons. So this must be the reduction part, and over here must be some oxidation. Iodine's going from a negative to 0. Okay, so it's getting more positive. Getting more positive means you're oxidizing, you're losing electrons. All right, these are my 2 halves, and I'm now going to add them back together. But the problem is actually now these electrons, you can't ever just have free floating electrons written in your expression. And I know it just feels like I'm making up rules, but these are the rules. What we need to do before we add these back together is we need to cancel these electrons. I have electrons on the left over here, electrons on the right over here. But I need to make it so when I add these 2 things back together, those cancel out. So what I need to do is actually multiply this whole side by 3. 6 iodines turn into 3 I2s plus 6 electrons. Okay. Now I'm going to attempt to add these 2 reactions back together. So I'm going to take this whole reaction and I'm just going to kind of add it here. Okay, so I made my addition here. Everything on the left side of the arrow, you'll put on the left side. Anything on the right side, you'll put on the right side. But you can cancel out anything that's on the left and right, like those 6 electrons and those 6 electrons. Usually other things cancel as well, but in this case, nothing actually does. So I'm just going to start listing my reactants. 6H plus ClO3 minus plus 6I minus. Those are all the things on the left. Yields Cl minus 3 H2Os, 3 iodines. That is your answer. That is your fully balanced reaction. If you check, you have the same number of hydrogens on both sides, oxygens on both sides, iodines on both sides, and if you add up the total charge, this is 6 plus, 1 minus, 6 minus. All that equals 1 minus together. Equals the charge over here, all I have is 1 minus. So now your charges on each side also equal. That is how you fully balance a redox reaction. Okay. It says in acidic solution, there's actually a couple more steps where I could give you basic solution, but we'll just ignore it. So that's just one example. I'm not going to have you do this full process, except for maybe like one or twice, but I won't have you do it on your full test. All right, so like I was saying, you don't need to know how to do this full problem, but there are a couple concepts that are important from it. Redox reactions are transfers of electrons. The numbers of electrons gained must equal the amount lost. The number of atoms on each side must still be equal. And this last idea is what's important. You can split reactions into oxidation and reduction half reactions to allow you to kind of balance them. I've not seen them ask a full problem like this. I don't think you're responsible for it. But I have seen them ask you to do a half reaction. Meaning, they could give you like one half like this and have you try to balance that. Not doing the whole process of adding them back together, but just like canceling it out like this. So because of that, I'm going to have you do a couple, but I wouldn't focus too much on it. That's all redox reaction stuff. Last thing we need to talk about today is acids and bases. So we have a whole unit on acids and bases later, but today we're just introducing the types of reactions they do. An acid is a proton donator. So that's what an acid is by this definition. Acids are just things that when they react, lose a proton, also known as an H+ ion, when they react. An H+ ion is a hydrogen ion with no electrons. Right? Hydrogens normally have one proton and one electron, and that's it. If you add the positive charge, it loses that electron, and literally it's just a proton. That's all you have left. Hydrogens also don't have neutrons. So an H+ is literally just a proton. So we'll call them the same thing interchangeably. The free H+ ions that an acid produces is what actually causes something to be acidic. The pH scale measures the amount of H+ in a liquid. And that's all the pH scale is doing, is how much H+ was made. Really powerful acids make a whole lot of H+. The H+ is the thing that is corrosive, that causes your skin to burn, that reacts with you. It is the thing that is actually doing the work. The acid itself is supplying H+ ions to do it for them. Acids are usually written with a hydrogen in front to help you understand that it's an acid. Also, if you write out the name of an acid, it's really obvious that it's an acid because almost all of them say like acetic acid or hydrochloric acid or sulfuric acid. It literally has the word acid in it. So that's also a way to know something's an acid. Or in a reaction, you can identify it as something that loses an H+. So if something starts with an extra hydrogen and an extra positive charge, and after it reacts, it's missing one of those, then you know it was an acid. It acted as an acid in that reaction. Okay, to start, switch to my acid notes over here. We're going to write the dissociation reaction of 3 acids. A dissociation reaction looks just like this. You are simply taking your acid and it is breaking down into its 2 products. Dissociation means literally to split apart into your ions. So in this case, hydrochloric acid, HCl, when it reacts, it loses an H+. It is a proton donator. All that's left is this chlorine, and this stole a positive charge away, so to make sure my charges are good, the chlorine has a negative now. So hydrochloric acid splits apart into hydrogen plus and chlorine minus. HNO3 is called nitric acid. This loses its H+, and the rest of it, NO3, with its minus charge, is left. And then I have H2O. H2O is an amphoteric molecule. It can sometimes behave as an acid and sometimes behave as a base. If you notice, it starts with an H, which kind of gives you that hint that it's an acid. And that's actually one of the reasons we write H2O in this way. But it'll lose an H+, and you'll be left with an H and an O. But this, for some reason, is usually flipped around to be OH with a negative. And the reason why is you might recognize this as hydroxide. So that'll be relevant later. So OH minus, we write it backwards this way because that's more familiar. right? And that's basically how you write the dissociation of an acid. You break it down to lose an H plus and write whatever is remaining. I have 3 reactions here. We want to look for the acid. So number 1, I have HF. Okay, my instinct is that this is probably the acid because it starts with an H. But so does H2O. So I can't really use that to figure out which thing is the acid here. So let's look at what happens during the reaction. I start with HF, and this turns into F minus. So HF lost an H and a positive charge to turn into F minus. Something that loses an H plus is the acid. So HF is the acid here. So you'd circle HF. If you look at H2O, it turns into H3O plus. So it's not losing a hydrogen, it's actually gaining a hydrogen, which is what a base is. So hydrogen is actually acting as a base this time. Next problem, I have NH3, which is ammonia, reacting with H2O. So NH3 doesn't start with the letter H, so it's probably not an acid. Okay. And if we check, NH3 turns into NH4 plus. So it is gaining an extra H and a positive charge, meaning it's a base. Ammonia is a very common base we use all the time. So H2O this time, H2O turns into OH minus. It loses one of its H's and it loses a positive charge. H2O is the acid in number 2. And number 3, we have H2SO4, starts with an H, good sign that's probably what's going on, NaOH, making H2O, and Na2SO4. This reaction is a little bit different than the top 2. This is a neutralization reaction. H2SO4 is reacting with this base, and these kind of work like a double replacement reaction. Okay, so H and OH bond together to make H2O, and NaSO4 bond together to make this Na2SO4. So it's a little bit harder to tell, but H2SO4 starts with H and ends, the SO4 loses both the H's. This one actually loses 2 H's, and because it's called a diprotic acid. It has 2 hydrogens like this written in the front is a hint it's going to lose 2 hydrogens when it reacts. But more on that later. Now, bases are the opposite. As I hinted before, they are proton acceptors. Bases gain a hydrogen during a chemical reaction. We saw that a couple times in those examples. Alternatively, though, there's another way to think about a base. And they end up being the exact same, but they don't sound like they are. Bases can be defined as a hydroxide, OH minus, donator. So bases either, you can write them as giving up OH minuses or gaining H's. And it turns out that kind of means the same thing. Okay. Let's save that for class. Both these definitions are true, but depending on the structure of the base, one is more apparent than the other. So I'm not trying to just be confusing by giving you 2 definitions. Sometimes one will be obvious, sometimes the other will be obvious. And it just depends on what type of base you're dealing with. So I'll try to give you some examples that make that clear. The strength of a base is just how much OH minus is present in the solution. All right, circle the base in each of these reactions. And these are the same 3 reactions, so it should be easy to find the bases. H2O gets an extra H and a plus. And number 1, H2O is my base. Number 2, I have NH3. NH3 turns into NH4. That's our base. It gains that H plus. And last, number 3, NaOH, okay, is turning into OH. It's kind of hard to tell what it turns into, okay? And this is where the other definition will come in handy. And this is where kind of recognizing common ones is helpful. The other way to recognize a base is that it starts, or it ends, with OH. But that's not always the case. Sometimes bases look like NH3, sometimes they look like H2O, and sometimes they look like NaOH, and it's kind of hard to tell. And that's one of the skills we'll have to practice, is recognizing that. NaOH you definitely will recognize because we're going to use it constantly. H2SO4, sulfuric acid, you'll recognize as well. So it's a little bit harder to tell when you mix a strong acid and base like this because their reaction can look a little bit weird. What we want to do here is identify each of these compounds as acids, bases, or salts. I'm going to kind of go through this list over here and tell you how I would recognize each one. Ends in OH means that it is definitely a base. Yeah, I feel good about that statement. Okay. HCl, starting with H, means it's probably an acid. Those are your number 2 indicators, and we intentionally write them this way. All right, KBr. So this is a little bit weird. K is just a metal, and this is just a non-metal. They're just mixing together. This is the definition of a salt. There's no hydrogen or hydroxide involved, so it can't be an acid. H2O, you could put it's an acid, but you could also say it's a base. Okay. If we go back here, we can kind of think about the definition of a base, of being either a hydrogen acceptor, which we saw in some of our problems, but here, H2O creates hydroxides. So H2O is a base because it makes these. It's an acid because it makes H+, but it's also a base because it makes hydroxides. So water is an example where you need donating hydroxides to show you that it's a base. HClO3, I see it starts with an H, I'm thinking acid. NH3, this one doesn't really follow any of our patterns, but it's a very common one you should definitely learn if you don't know it already. You should probably know its common name, ammonia, and the fact that it is a base. That one you just kind of have to know. CaOH2, it ends with OH. I'm thinking it's a base. And that's really what you're looking for, right? Starts with an H, definitely an acid. Ends with a base, or OH, definitely a base. And then some of them you just kind of have to know, which is annoying. Why we'll practice it a bunch. When acids and bases react with each other, they neutralize each other. Acids and bases produce water and salts when you mix them together. So here I have hydrochloric acid, sodium hydroxide, very strong acid, very strong base. If you mix them together with equal amounts, you end up with only water and salt, just regular old salt. You make salt water. So you're not making anything dangerous. Same thing here, you have strontium hydroxide, that's a base, mixing with hydrobromic acid, HBr, and you make this salt. Notice how it doesn't have any H's, it's definitely a salt, and H2O, water. Acid is completely neutralized by an equal molar amount of base. That's kind of a weird word you might see pop up on like an AP exam. Equal molar means you have the same amount of moles. It's just a very concise way to say that. So if I have 10 moles of acid and add 10 moles of base, those are both gone. They are neutralized. You would expect the pH to be 7 or very close to it. Okay. How many milliliters of 0.25 molar base should I add to 65 milliliters of 0.15 molar acid to neutralize it? Do not get overwhelmed by the numbers and the questions. We're looking for patterns here so we can kind of recognize what we're doing. So I'm just going to start by kind of jotting down the information and trying to organize it to see where I need to go. All right, so we're working down here. The problem told me I had 0.025 molar base. So that tells me how strong my base is. When I think molarity, I'm probably going to have to use my molarity formula at some point. So I'm just going to jot that to the side for now. It also told me some information about my acid. It said how much acid I had and how strong it was. Okay, it says that these things completely neutralize each other. What that means, that extra piece of information, is that the moles of acid that you find is exactly equal to the moles of base you have. And that just means if you're somehow able to find the number of moles of acid you have, you can also know how many moles of base. You know that they're equal because they completely neutralized each other. Now, the question wants to know, how much base do I need to neutralize this much acid? I have more information about my acid here. So I'm going to start with this. I know how strong it is. I know how much I have. I can use the molarity formula to find out how many moles of acid I have exactly. So I'm going to start by doing that. 0.15 molar equals moles over, and I'm just going to convert this to liters by dividing by 1,000. So it's like 1, 2, 3. 0.065 liters. And then I'm going to pull out my calculator, do 0.065 times 0.15. I know I have exactly this many moles of acid. And I'm just calling it acid. It's generic. It doesn't matter which acid I have. Okay? So that's exactly the amount of acid I have in my situation. Okay? This is how strong it was. This is how much I had. I use that to find how many moles of it is. And then that also tells me how many moles of base. Because they're neutralizing each other, I need the same amount of moles of each one. Okay, so that's the first part of the problem. I now know exactly how much base I must have had based on how much acid it took to neutralize it. The second piece of information I have is I know how strong my base is, 0.025 molar. Because I just found out how many moles of it I have, 0.00975, I can divide it by liters. I'm just using this formula again to find how many liters of it I have. And then just turn it into milliliters. Multiply liters up here. Solve for liters by dividing by that 0.025. 0.39 liters, which is 390 milliliters. Because the problem asks for milliliters specifically. Okay, and that kind of makes sense, okay? I have 65 milliliters of this acid. My acid is 0.15 molar, so it's a decent amount more concentrated than my base. My base is only 0.025 molar. So it kind of makes sense. I have 65 milliliters of this kind of strong acid and 390 milliliters of this a little bit more diluted base. And those add up to cancel each other out. Okay. Another way to ask, how many grams of baking soda, which is a base, do I need to neutralize 25 grams of hydrochloric acid? Okay, so 25 grams of hydrochloric acid, and I want to neutralize that. Okay, that means when you see neutralize, just always think, okay, the amount of acid, the moles of acid I have must equal moles of base. Well, I have grams of acid. I can easily turn that into moles of acid. All I have to do is a gram to mole conversion. One-step train track. Grams of hydrochloric acid under moles of hydrochloric acid. 1 mole of HCl weighs, this is 35 plus 1. We'll just round it for simplicity to 36. 25 divided by 36. 0.694 moles of HCl. So that's how many moles of acid I have. But that's also how many moles of base I have because we have a neutralization. So I'm going to squeeze it down here. I know I have 0.694 moles of baking soda. Baking soda's formula is NaHCO3. I wouldn't expect you to know that. We do use it occasionally, but that's okay. I just need to convert this to grams. The problem is asking how many grams of that I need. So I have moles. I'll just convert it to grams. Moles to grams. 1 mole. This is 23 plus 1 plus 12 plus 48, 60 plus, that's 84. Just take my number, times 84. 58.3 grams of baking soda. Which is kind of cool. I know how much acid I have of 25 grams of it. I was able to use some math to figure out exactly how many grams of baking soda I need to throw on top of my acid to neutralize it. And that would get rid of all of the acidity and basicity. Right? Okay. Acid and base reactions involve a transfer of a proton, right? You're losing and gaining a proton, or more than one, right? So redox reactions are about moving an electron. Acid-base reactions are about moving a proton. The acid will lose an H plus, the base gains it. And that will help you write your two products. So we have a couple of examples here of writing reactions of neutralizations. HNO3 reacts with NH3 is an acid and a base reactant. So that tells you they're reacting. They are your two reactants. Okay. HNO3 is going to lose an H. It's going to give its H over to the base. Okay. So you'll be left with some NO3 minus. The H goes over to NH3 to make NH4 plus. You are transferring a single proton over to that. That's your reaction. Okay. I think it's relatively easy. It looks weird when you get some weird acids and bases, but for one like this, it works out really nice. Second problem. So next slide just has another problem. Down here, HF reacts with NaOH. I kind of left out this logic, I guess, but I understand this is the acid because it starts with an H. So just like last time, it's H. It's going to give it to NaOH. So you'll be left with F minus and NaOH 2 plus. You add an H, you add a plus. Okay. That's not our final answer here, though, because this is not something that really exists. You'll never see it written like this. How you'll see it written instead, if you have an OH2, which we normally would just like write as like H2O, right? That H2O actually separates off of the sodium and it ends up looking like this. So the left side will stay the same. You have an F minus. The Na takes the positive charge because that helps it satisfy the octet rule. And then that H2O floats around by itself. So you might see it written like that. Okay, but now you have a positive and negative ion. So you might also even see it like this, where we just combine those two together to make NaF and H2O. So there's three different ways that I could have written this reaction. They're all equally valid. This top one's kind of icky. You wouldn't ever see it written like this because this is a weird compound that you wouldn't see in real life. You might see it like number 2, but you'd most common see it like number 3. So an easier way to get there, and this works best whenever you have an OH compound, because OH ones are weird. Just skip all of this, and I'm going to rewrite it over here. So if you ever get to this point where there's a weird icky thing and you want to avoid it, just treat this like a normal double replacement reaction. The H goes to the OH, and the Na goes to the F. You make H2O and NaF. Acid-base reactions are really just double replacement reactions, but they're a little bit special. And that's it. You have the same products. I flipped them this time, but you have the same products here and here. So that's an alternative way to write a neutralization, and that'll be beneficial when you have a base that ends in OH. If you notice in the first one, we had NH3, which works a lot better. Okay. That's some examples of how to write different reactions. A lot more practice of that to come, don't worry. Bringing us to our last topic, titrations. A titration takes advantage of the math concepts of a neutralization reaction to help us learn more about an unknown sample. If you have an acid, but you don't know its concentration, you can figure it out by using some of this math we were just learning. We actually already did the math on the previous page there, right? When we were talking about how many milliliters of base I need to neutralize some acid. We're doing the same thing here. We're just applying it directly to like a lab concept. When your acid is perfectly neutralized, we have this statement again, moles of acid equals moles of base. Okay. Now, to help us in the actual experiment of a titration, we need to know when something is neutralized. The easiest way is to use an indicator like phenolphthalein. Okay? Phenolphthalein turns pink when it is basic. So if its pH is above 7, it turns bright pink. And I think we've used this a little bit before. Okay? But if it's acidic at all, it's colorless. So it turns pink just when it becomes neutralized and above. So if you're able to just turn it the slightest little bit of pink, you have perfectly neutralized your solution. Now, that's way cooler than the other method, which is just using like a pH probe to wait until the pH gets to 7. That's also a method you could use, but the phenolphthalein is way cooler. All right, so we have a couple examples to end this with, and that's the last bit of notes, but let's do these 2 examples real quick. I have 25 milliliters of HCl, so I have an acid, and I don't know its concentration. I titrate to the equivalence point. The equivalence point is just when it is neutralized. With 28 milliliters of some base, and it tells me how strong it is. What's the concentration of my acid? Again, I'm just going to jot down my information for my problem. I have 25 milliliters of some strength hydrochloric acid. I don't know how strong it is. That's my goal, is to find out how strong it is. Okay, I know how much base I have, 28 milliliters of it, so that's my volume. This is how strong it is. I need to use that to find how much of this I have. Just like before, we're using this relationship, mole of acid equals moles of base. So hopefully you're noticing a pattern with how we're solving this. Okay, I know information about my base. I can use that to find out how many moles of it I have, which tells me how many moles of acid I have, which I can use to find more information about my acid. Okay, I am going to give you a shortcut method you can use for this time. If you recognize this formula, M1V1 equals M2V2, we usually call this the dilution formula. Okay. The idea, though, is that M1 times V1 just gives you moles. Moles that you start with, moles number 1. M2 times V2 gives you moles number 2. We're just rearranging the molarity formula. Molarity times liter gives you moles. So you can use this instead. Just make M1V1 about your acid and M2V2 about your base, and you can just use molarity and volume this way to speed up your problem. Okay, so like over here, the acid, I know its volume, but I don't know its molarity. M1 is its molarity. V1, the best part about this, you don't even have to convert the units, as long as you use the same unit on either side. So I'm just going to put 25 milliliters there. M2, this is my information about my base. I know how strong it is, 0.12. I know the volume I have is 28 milliliters. If I just solve this expression, that's my answer. So that's a nice shortcut you can use. Anytime you're looking at a neutralization or a titration like this, you could have done the exact same method back here. We're basically doing the same thing, except we're doing it all at once. Okay, so I'm going to solve this. So solve this in one go. 0.12 times 28, simplify that side, divide it by 25. There's my answer. 0.1344 is the molarity of my acid. Okay, so that's a shortcut you can use to solve a problem like this. And that number kind of makes sense, okay? I have 25 milliliters of this and 28 milliliters of this, so their molarity should be relatively close. 0.12 and 0.13 are pretty close. Which brings us to our last problem. Okay. I have 36 milliliters of acid, and this time I know how strong my acid is. So I have both pieces of info about that hydrochloric acid, because I wrote acid twice, are titrated to the equivalence point. So we have the same moles of acid and base at the equivalence point, and with 1.0 molar NaOH. How many milliliters of NaOH should it take to reach that point? So this time, I know how much acid, I know its strength. My base, I know its strength, I don't know how much I have. I think it's really helpful to write out a problem like this with just this information. Just writing which piece of information I have for which chemical. It'll save you a lot of trouble making sure all your thoughts are organized. Solving it, we're going to use that same shortcut. Use this anytime, it always works. M1 your molarity 1, I'm going to make it for my acid. If you made M1V1 for the base and flipped it, it wouldn't matter. 1 and 2 are arbitrary, but I usually like to put the acid over here and the base over here to be consistent, but it doesn't matter. So I have 2.5 molar acid, and I have 36 milliliters of it. My base, I know I have 1 molar, and I don't know its volume. But I can solve it. 2.5 times 36 divided by 1, 90 milliliters is how much volume I need to neutralize it with. Okay, the only problem I have with this method is that it kind of takes you out of the problem, I feel like. You might not quite understand what's going on. Okay, I think working it all out was better to show you first, just because you can kind of see how your numbers add up and you're actually talking about this relationship specifically in the problem. Mole of acid equals moles of base. So that is important. Make sure you're keeping this in mind. I don't care if you use the shortcut, but know the shortcut is based off this principle. Okay? And that's essentially what you're saying here. Moles of acid equals moles of base. All right. And that is all for today. All right. Hopefully most of that sort of made sense. We learned those 2 different types of reactions. And this has been over an hour, so you see why I cut these 2 out, made their own separate lesson. All right. All right. Thank you for watching. I'll see you later.